In Chapter 6, Section 3, we will do a review of sampling distributions and estimators. Up until this point in statistics, we have been plotting graphs for sets of numbers. In Chapter 6, we will learn about sampling distributions. A sampling distribution is a graph of a statistic for your sample data. While technically you could choose any statistic to paint a picture, some common ones you'll come across are mean, variance of sample, standard deviation of the sample, and proportions. We will also learn about estimators. An estimator is a statistic that estimates some fact about the population. You can think of an estimator as the rule that creates an estimate. For example, the sample mean is an estimator for the population mean. In this section, we'll consider the concept of sampling distribution of a statistic. Instead of working with values from the original population, we want to focus on the value of statistics, such as sample proportions or sample means, obtained from the population. When samples of the same size are taken from the same population, the following two properties apply. Sample proportions tend to be normally distributed, and 2, the mean of sample proportions is the same as the population mean. Let's consider the sampling distribution of the sample proportion. If repeated random samples of a given size n are taken from a population of values for a categorical variable, where the proportion in the category of interest is p, then the mean of all sample proportions, known as p hat, is the population proportion p. In other words, if we could find the sample proportion of every possible sample from a given population, and we were to plot each of those sample proportions, then if the population were large enough, the distribution of all the sample proportions might be approximately normally distributed. The sampling distribution of the mean is the mean of the population from where the items are sampled. If the population distribution is normal, then the sampling distribution of the mean is likely to be normal for the samples of all sizes of n. In other words, if we could find the sample mean of every possible sample from a given population that is normally distributed, and we were to plot each of those sample means, and if the population were large enough, then the distribution of all sample means might be approximately normally distributed. In general, when samples of size n are taken from a normal distribution with variance sigma square, then the sampling distribution of the sample variance tends to have a skewed distribution. This skewed distribution is also known as a chi-square distribution with n-1 degrees of freedoms. We can formally define a sampling distribution as follows. The sampling distribution of a statistic, such as a sample proportion or sample mean, is the distribution of all values of the statistic when all possible samples of the same size n are taken from the same population. The sampling distribution of a statistic is typically represented as a probability distribution in the format of a probability histogram, or a formula or a table. We can formally define a sampling distribution of a sample proportion as follows. The sampling distribution of a sample proportion is the distribution of sample proportions, or the distribution of the variable p hat, with all samples having the same sample size n taken from the same population. The sampling distribution of the sample proportion is typically represented as a probability distribution in the format of a probability histogram, formula, or a table. Let's review some notation for proportions. We need to distinguish between a population proportion P and some sample proportion. So we can say P equals to the population proportion, while P hat is equal to the sample proportion. When symbols are used above the letters, as in P or as in X bar or P hat, they represent statistics and not parameters. Behaviors of the sample proportion can be described as follows. First, the distribution of sample proportions tend to approximate a normal distribution. And second, sample proportions target the value of the population proportion in the sense that the mean of all the sample proportions P hat is equal to the population proportion P. The expected value of the sample proportion is equal to the population proportion. Let's consider the following example. Consider repeating this process. Roll a die 5 times and find the proportion of odd numbers, 1, 3, or 5. What do we know about the behavior of all sample proportions that are generated as the process continues indefinitely? This figure illustrates a process of rolling a die 5 times and finding the proportion of odd numbers. The figure shows the results from repeating this process 10,000 times, but the true sampling distribution of the sample proportion involves repeating the process indefinitely. The figure shows that the sample proportions are approximately normally distributed. Because the values of 1, 2, 3, 4, 5, and 6 on the die are all equally likely to occur, the proportion of odd numbers in the population is 0.5, and the figure shows that the sample proportions have a mean of 0.5. The sampling distribution of the sample mean is the distribution of all possible sample means, or the distribution of the variable X bar, with all samples having the same size n taken from the same population. The sampling distribution of the sample mean is typically represented as a probability distribution in the format of a probability histogram, formula, or table. Behavior of the sample means can be described as follows. First, the distribution of sample means tend to be a normal distribution, and we will discuss this further in the next section. But the distribution tends to become closer to a normal distribution as the sample size increases. And second, the sample means target the value of the population mean. That is to say, the mean of the sample means is the population mean. The expected value of the sample mean is equal to the population mean. Let's continue with our example of rolling a die. Consider repeating this process. Roll a die 5 times to randomly select 5 values from our population of possible values 1, 2, 3, 4, 5, or 6. Then find the mean of the results. What do you know about the behavior of all sample means that are generated as this process continues indefinitely? The figure illustrates a process of rolling a die 5 times and finding the mean of the results. The figure also shows results from repeating this process 10,000 times, but the true sampling distribution of the mean involves repeating the process indefinitely. Because the values of 1, 2, 3, 4, 5, and 6 are all equally likely to occur, the population has a mean of mu equals to the sum of x over n, which is equal to the sum of 1 plus 2 plus 3 plus 4 plus 5 plus 6 divided by 6 is equal to 3.5. The 10,000 sample means included in the figure have a mean of 3.5. If the process is continued indefinitely, the mean of the sample means will be 3.5. Also, the figure shows that the distribution of the sample mean is approximately a normal distribution. The sampling distribution of the sample variance is the distribution of sample variances, the variable S², with all samples having the same size n taken from the same population. The sampling distribution of the sample variance is typically represented as a probability distribution in the format of a table, probability histogram, or a formula. Recall that the population standard deviation is equal to sigma equals to the square root of the sum of x minus mu squared divided by the population size n. And the population variance is equal to sigma squared is equal to the sum of x minus mu quantity squared over the population sample size, the population size n. The behavior of the sample variances can be described as follows. First, the distribution of sample variances tends to be a distribution skewed to the right. And second, the sample variances target the value of the population variance. That is to say, the mean of the sample variances is the population variance. The expected value of the sample variance is equal to the population variance. Continuing on with our example of rolling a die, let's consider repeating this process. Roll a die 5 times and find the variance S² of the results. What do we know about the behavior of all sample variances that are generated as this process continues indefinitely? The figure illustrates a process of rolling a die 5 times and finding the variance of the results. The figure also shows the results from repeating this process 10,000 times, but the true sampling variance of the sample variance involves repeating this process indefinitely. Because the values of 1, 2, 3, 4, 5, and 6 are all equally likely to occur, the population has a variance of sigma square equals to the sum of xi minus mu quantity squared over the population size n. If we run that calculation, it is approximately equal to 2.9. And the 10,000 sample variances included in the figure have a mean of 2.9. If the process is continued indefinitely, the mean of the sample variances will be 2.9. Also, the figure shows that the distribution of the sample variance is a skewed distribution and not the normal distribution. An estimator is a statistic used to infer or to estimate the value of a population parameter. An unbiased estimator is a statistic that targets the value of the corresponding population parameter in the sense that the sampling distribution of the statistic has a mean that is equal to the corresponding population parameter. In other words, an unbiased estimator is an accurate statistic that is used to approximate a population parameter. Accurate in this sense means that it's neither an overestimate nor an underestimate. If an overestimate or an underestimate does occur, the mean of the difference is called a bias. These statistics are unbiased estimators. That is to say, they each target the value of the corresponding population parameter, with the sampling distribution having a mean equal to the population parameter itself. So we say the proportion p hat is an unbiased estimator of the population proportion p. and the mean x bar is an unbiased estimator of the population mean mu, and variance S square is an unbiased estimator of the population variance sigma square. On the other hand, these statistics are biased estimators. That is to say, they do not target the value of the corresponding population parameter. These include the median, the range, and the standard deviation S. The bias of an estimator is the difference between the statistic's expected value and the true value of the population parameter. If the statistic is a true reflection of a population parameter, it is an unbiased estimator. If it is not a true reflection of the population parameter, it is a biased estimator. All of the previous examples in this section involved sampling with replacement. Sampling without replacement would have the practical advantage of avoiding wasteful duplication whenever the same item is selected more than once. However, many statistical procedures we will discuss in the next chapters are based on the assumption that sampling is conducted with replacement because of two very important reasons. First, when selecting a relatively small sample from a large population, it makes no significant difference whether we sample with or without replacement. And second, sampling with replacement results in independent events that are unaffected by previous outcomes. And independent events are easier to analyze and result in simpler calculations and formulas.